ሰላም ሰላም እንዴት ናችሁ? እንኳን ወደዚህ ቪዲዮ በደህና መጣችሁ። ዛሬ በድጋሚ ተመልሻለሁ። ዛሬ የተመለስኩት በቤዚክ ማትማቲክስ ፎር ናቹራል ሳይንስ ወርክሽት ሶሉሽን ይዤ ነው። ይህ ወርክሽት ቻፕተር 2 ላይ የተዘጋጀ ወርክሽቱ ነው። ስለዚህ ከዚህ ወርክሽት የተወሰኑ ሳምፕል ጥያቄዎችን ሶሉሽን አብረን ያለን ማለት ነው። ስለሆነም በቀጥታ ወደ ቪዲዮቹ ወይም ደግሞ ወደ ጥያቄዎቹ ከመሄዳችን በፊት ምናልባት ለዚህ ቻናል አዲስ የሆናችሁ ሰዎች ካላችሁ ቻናሉን ሰብስክራይብ በማድረግ እና ቪዲዮንም ላይክ በማድረግ እንድትጀምሩ አበረታታለሁ። በመቀጠል ወደ ጥያቄዎቹ እሄዳለሁ። የመጀመሪያው ጥያቄ using a principle of mathematical induction, we are asked just to prove 5n plus 5 less than or equal to n square for every n greater than or equal to 6. So in order to prove such a theorem or simple statement by using a principle of mathematical induction, we have steps. The base case, inductive hypothesis, and the last one is inductive step. So the first one, that is best case, could be just proving or checking the truthiness of the statement for the first few elements of n. In this case, the first value of n is 6, so that let us check for n is equal to 6. So directly, if we substitute 6 in the place of n, here we have 5 times 6 plus 5 is equal to 35, which is less than or equal to 36, which is 6 square. So it holds true for the first value of n, that is n is equal to 6. Then depending on the base case, the second step within this mathematical induction would be inductive hypothesis, that is simply assuming the statement holds true for an arbitrary natural number, that is k. So we must assume that 5k plus 5 is less than or equal to k for some k greater than or equal to 6. That means for an arbitrary natural number k, we have to assume that 5n plus 5 is less than or equal to this one, that is k square. Then based on this assumption, what we are asking, or simply what we need to show here, is that we must show that the theorem holds true for also for the next natural number, that is k plus 1. To do this, for k plus 1, if we directly substitute k plus 1 in the place of n, here we have this one, that is 5 into k plus 1 plus 5, which is equal to 5k. That is, if you distribute this 5 over k plus 1, you have 5k plus 10. And then, which is less than or equal to k square plus 5 from the hypothesis that already we have here. But in this case, we have still less than or equal to k square plus twice of k plus 1, because this one, that is twice of k plus 1, and because of this one, that simply is k greater than 6, 5 less than 2k plus 1. 5 less than or equal to twice of k plus 1, that is twice of k plus 1 is greater than or equal to 5, so that k square plus 5 is less than or equal to k square plus twice of k plus 1. Because of this one, that simply this 5 is less than or equal to twice of k plus 1. Then this one, that is k square plus twice of k plus 1, is a perfect trinomial, that is, which is the square of k plus 1 square. Therefore, if you observe a statement that is the form of this statement with k plus 1, 5 times k plus 1 plus 5. This is, which is the equivalent with, that means this is identical with k square plus twice of k plus 1, but this k plus 1, the whole square, is less than or equal to 5 into k plus 1 plus 5, so that it is true by using that of induction or simple mathematical induction. The statement holds true for n greater than or equal to 6. The next one, that is question number 2, that is question number 1b, will be again on principle of mathematical induction. Using principle of mathematical induction, prove that twice of n plus 1 is always less than or equal to twice of 2 the power of n for every n greater than or equal to 3. Again, we have to follow the previous 3 steps that already we have seen previously. So that in this case, and the first step would be checking that is the best case. The best case, that's simply for the first value of n here is 3. So that we have to check whether this statement is true for n is equal to 3. So directly substituting n in the 3 in the place of n here, we have twice of 3 plus 1 is equal to 7. Again, this 7 is less than or equal to 8, which is 2 cubed. So that the statement holds true for n is equal to 3. Then after checking this one, we have to proceed to the inductive hypothesis. The inductive hypothesis is simply assuming that the statement holds true for an arbitrary natural number which is greater than or equal to this one, that is 3. So that's, let's assume that twice of k plus 1 less than or equal to twice of k for some k greater than or equal to this one, that's simply 3. Then based on this assumption, the next or simply the next step would be inductive step, which is checking for the truthiness of this statement for k plus 1 or the next natural number that is k from this assumption. Then directly, if we substitute k plus 1 in the place of n, here we have twice of k plus 1 is equal to twice of k plus 3. This is twice of k plus 3. So if we factor out this one, that is twice of k plus 1, that is dividing this one, that's simply 3 into 2 parts 1 and that of 3, that is 1 plus 3, we have this one. Then this one, twice of k plus 1 plus 2 is less than or equal to twice of k plus 2. By the hypothesis that simply here what we have here is twice of k plus 1 is less than or equal to twice of k. So that we have twice of k here plus 2 here. Therefore, there is less than or equal to twice of k plus twice of k. Since twice 2 is less than or equal to the power of k for k greater than or equal to 1. Then if we factor out to the power of k the common factor we have, or simply this one, that's simply twice of k. His identical is twice of k plus to the power of k plus to the power of k, which is yeah, 2 times to the power of k plus 1, which is to the power of to the power of k plus 1. Therefore, there is the last one, that's simply by using the mathematical principle of mathematical induction. The statement that is to the power of n plus 1 less than or equal to the power of n holds true for every n greater than or equal to 3, because directly we are assuming for the statement is true for k, or an arbitrary k, so that we are able to show that the theorem holds true for the next natural number that is k plus 1, so that is the approach. The next one, that is question number 2a. Find the LCM of the smallest one-digit composite number and the smallest two-digit composite number. You know that the LCM of the given any two or more natural numbers will be obtained by either prime factorization method or listing method. But here, in this case, we are not directly or simply explicitly given the given digits or simply numbers. What we are given here is we are given the smallest one-digit composite number and the smallest two-digit composite number. So we have to know these to first just before we try to calculate their LCM. We know that the smallest one-digit composite number is 4. There is no any other one-digit number which is less than that of this one, which is a composite which is less than that of 4. And the smallest two-digit composite number is said to be 10. Therefore, we are asked just to calculate the least common multiple of these two. The least common multiple of these two could be I think this one that's simply 20, because here is 2 square and this one is 2 times 5. So that from 2 square we can take that is 2. And that means the highest one, that's simply 2 square, and from 5, even though it's not a common factor, we have to take, so that 2 square times 5 becomes this one, that's simply 20. Therefore, the least common multiple of a one digit, the smallest one digit number and the smallest two digit number, that is 4 and 2, is exactly 20. The next one, that is question number 2C. A school has 45 boys and 60 girls. The principal wants us to divide into the largest possible equal groups containing both boys and girls. How many students will be in each group? What we are given here is we are given pupils or simple schools, boys and that of girls, which are 45 and 16 respectively. And the principal of the school wants us to divide this into the largest possible equal groups containing both boys and that of girls. Then how many students will be in each group in the question? So that is again the application of a greater common factor. So that's at the greater common factor of both the boys and the given number of girls, that will be the maximum, or simply the largest possible equal groups containing boys and girls. So that's the greater common factor of 45 and 60 is 15. So that the largest possible equal groups containing boys and that of girls will be this one, that is 15 students. That means the largest equal group contains 15 students each. So that the next one is question number 3, which is about an upper bound and lower bound of a given set or simple interval. We are given that we are asked just to find the least upper bound and the greatest lower bound of this interval. If this is an open interval, which starts from 0 and goes to that of negative infinity. So that in order to do this, in order to calculate the bounds, we know that a certain point or simply real number is said to be the upper bound of the given set if and only if that number or simple real number is greater than or equal to that of every element of this set. So that any real number which is larger than that of every element of this set is said to be an upper bound for this set. Similarly, if there exists a certain real number which is less than or equal to every element of this set, so that that element is said to be the lower bound of this set. And that, by using that of completeness property, we know that if the set, or simply for any set which is a subset of set of real number, if the set has an upper bound, it must have least upper bound. If the set has lower bound, so that it must have greater lower bound. So that's it. Therefore, because this set is not bounded from below, but it is bounded from above, so that the set will have only an upper bound. Therefore, the upper bound of A could be a set that is simply x greater than or equal to that of there, including the raven. But it doesn't have a lower bound because it is unbounded from below. Because we don't know the smallest possible element of the set, so that it is unbounded from below. Therefore, it will never have lower bounds. If the set doesn't have a lower bound, it will never have greater lower bound too. Therefore, the least upper bound for this one could be, that means the smallest element of its upper bounds the upper bound is x greater than or equal to 0. The smallest element is 0, so that the least upper bound of this set is 0. But by using that of completeness property, since the set doesn't have a lower bound, therefore it will never have greater lower bound. That means the greater lower bound of the set doesn't exist. The next one, that's question number 3e. Again, it is on least upper bound and greater lower bound of a given set. We are given the set that simply set A in the form of this function that is 3 minus 1 over n, where n is an element of n, set of natural number. That means, so that we are asked just to find the least upper bound and the greater lower bound of the set. First, in order to determine the least and greater lower bound of the set, we have to know the property of the elements of this one. We know that when n is equal to taken to be the first natural number, that is 1, 3 minus 1 over 1, or simply 1 would be this one, that's simply 2. So that they hit the first element for this set, that's simply set A. Then the next one could be when n is equal to 2, 3 minus 1 over 2 could be 5 over 2. When n is 3, 3 minus 1 over 3, it becomes 8 over 3, which is an increasing, because this is decreasing when n goes to when n is increasing. Therefore, most probably when we assume that n is a very large positive natural number, so that 1 over n will tend to 0, and the whole expression of this formula, that is 3 minus 1 over n, will approaches to 3. Therefore, every element of this set will be bounded in between 2 and that of 3. Therefore, the lower bound of this set, that's simply set A, that is a real number which is less than or equal to that of every element of this one, could be x less than or equal to 2, and its upper bound will be the set containing x greater than or equal to 3. So that since this set has both an upper bound and lower bound, therefore it will have its own least upper bound and greater lower bound. So that the least upper bound of the given set could be, because the greater lower bound of this one is that simply x greater than that of 3, so that the smallest element within this set is taken to be the least upper bound of the given set E. And the greater lower bound could be the greater lower bound of the lower bound of the set, that simply set E, is x less than or equal to 2, so that from the set the largest or the greatest element could be taken as the greater lower bound of this one, so that 2 is the largest element, therefore the greater lower bound of this set could be 2. Next, question number 4. We are asked just write the complex number that is on the set of complex number 2 plus I multiplied by 3 minus 2i divided by 1 plus I in the form of x plus y, that is in standard form. Therefore, our first thing would be multiplying denominators together. When we expand this one, that is simply 2 plus I times this one, that is 2 times 3 is 6, 2 times minus 2 is minus 4i, I times 3, that is plus 3i, I times minus 2i could be, and that is, I think positive 2, that is I square is minus 1 times minus 2 is positive 2. So that when we simplify this one, we have 8 minus I, which is denominator. Now let's divide this one, that is 8 minus I, by 1 plus I. When we do this, that is in order to change this one into x plus I y form again, we have to multiply both denominator and the denominator of this fraction by the complex conjugate of this one, that is 1 minus I. So that we have this one, that is the product of 1 plus I and 1 minus I could be the square of the norm of this thing, so that it is 2. But this could be, that is denominator, the product, that is when we expand it, we have this one, that is 7 minus 9i. We have the denominator, that's 2 here. Therefore, the standard form of this, simplified form of this expression could be this one, that is 7 over 2 minus 9 over 2i, so that the real part, that is simply the value of x, and minus 9 over 2 could be the imaginary part of the the simplified form of this complex number, which is this thing. The next one, that's question number 40. Again, it is simplification of complex number, writing this expression in the form of x plus iy form again, that is in standard form. So if we follow the same procedure, the solution could be, first, let's take the cube of I, that is pure imaginary complex number. I cubed is simply I squared times I, that is I squared is minus 1 times I could be minus I. And let's again expand the numerator, that's simply 2 plus 2i times 1 minus I multiplied by I over I, that is the complete conjugate of this one. So that it is just 3 plus twice of I into 1 minus I over minus I square. This is, I think, this one, that simply this would be further simplified to this thing, that is 3 plus 3i plus 2i plus 2i square. Then the 2i square is minus 2 because I square is minus 1. Minus 1 times 2 will be minus 2. So that if we combine these two, we have 3 minus 2, that is, I think, 1, and 3 plus 2i could be, that is 5i. Therefore, 1 plus 5i, the simplified form of the given complex number. So that the standard form of this expression could be 1 plus 5i, where 1 is the real part and 5 is the imaginary part of this simplification. The next one is question number 40. It says write the following complex number. The complex number in power form in a standard form, that is x plus I y form. So that the solution will be, first we have to convert this one into polar form. That is, a polar form of a complex number means writing the given complex number as a function of r in theta. We know that first the r, that is the magnitude of the complex number, could be the square root of the imaginary part plus the real part of the complex number, that is, the real part is radical 3. It is a square plus minus 1, which is the imaginary part of this one, that is this one, that's simply 2, which is the square root of 4. And the argument, that simply theta, could be tan inverse or arctan of the imaginary part divided by the real part, that is minus 1 over radical 3. And this could be a negative angle, which is negative pi over 6. So that if we can obtain a range that of theta, we can write this one in the form of that of polar form as using this one, that's simply de Moivre's formula or simply theorem. We have to the power of 10, that is the power of this one, and that is r to the power of 10. That means then cosine of 10, the exponent multiplied by theta plus I times sine of 10, that is 10 is this one, that's simply the exponent multiplied by this one. Then when we further simplify this thing, we have to the power of 10 is, I think, about 1024. Then cosine of the product of these two, that is negative 5 over 3, 5 pi over 3, plus I times sine of negative 5 pi over 3. Therefore, this is the standard form of this thing. So that in order to determine x here, x means 1024 multiplied by cosine of pi over 3, and y means that is the imaginary part of this one, could be 1024 multiplied by sine of pi over 3, sine of pi over 3. Then the next one, the next question is 5a, that is we're asked just to solve the complex number z is equal to x plus iy. That is what we're given here is 4 plus 5i is equal to z minus 1 minus I. So that we are asked just to find the value of z which can make this equation to be true. Or just we are asked just to write z in terms of this one, or simply in standard form as in the form of x plus iy. So the solution will be just transferring or simply taking this one to the left of the equality sign, so that we have z is equal to 4 plus 5i, then plus 1 minus 4 I, and 1 minus I. That is the summation of two complex numbers. We know that in order to add two complex numbers, the sum of any two complex number is complex number, and it could be obtained by adding their corresponding real parts together and the imaginary parts together, so that the sum of these two complex numbers could be, that is 4 plus 1, that is the real part of the first, plus the real part of the second complex number is 5. And the sum of the imaginary part of this one, 5i plus minus I, could be this one, which is 4i. So therefore, z could be z could be 5 plus 4i. Next one, that is question number 5c. Again, it is solving this expression, this equation involving complex number in the form of z is equal to x plus iy. We have 3 plus 5i plus x minus iy is equal to 6 minus 2i. So in order to have this form, that is z is equal to x plus iy, we have to equate the imaginary and the real part of the given complex number. We have the real parts here, and the real parts could be the we have 3 here, x and 6, so that the sum of these two must be identical with the real part of the x plus iy, that is simply x, so that 3 plus x must be equal with this one, that is 6, which implies x is equal to, because it is linear, that the value of x will become 3. Similarly, from the imaginary parts, we have 5 here, minus the second imaginary part of this one, that's simply y, is equal to this one, that's simply minus 2. Therefore, here the value of y could be, that's taking this one into here and taking minus y to the left of the right of this one, so that we have y is equal to 7. Therefore, the function, the complex number that z could be in the form of x plus iy. That means the value of x is 3, the value of y is 7, so that it becomes z is equal to 3 plus 7i. Question number 6b. For the values of a real number x and y such that the complex number 3 minus ix squared y and minus x squared minus y minus 4i are conjugate to each other. So what we are asking here is, we are asked just to find x and y, where these two complex numbers are. One is the complex conjugate of the other. That means, you know that the complex conjugate of a given number, or simply complex number, is obtained by taking only or making the imaginary part of the given complex number to be a negative one, or its opposite. So that if z is equal to plus iy, that is, it is complex conjugate will be this one, that is a minus pi, and then 3 minus ix squared y is equal to, that means minus x squared minus y minus 4i, because if this one, that's 3 minus ix squared y, and this complex number are, one is the complex conjugate of the other, so that in order to make equal, the complex conjugate of either of these two must be identical with the next one. So therefore, if we take this one, this complex conjugate. Again, if we take the conjugate of the complex conjugate, it must be identical. That's simply the double conjugate. So that must be minus x squared minus y, just taking this one to be the opposite, plus 4i. And then equate the real and imaginary parts together. That is this expression and this one. We have the real part for this one is 3. The imaginary part is x squared y. The real part for this one is minus x squared minus y, and the imaginary part is 4. So if we equate this expression, we have this one, that's 3 is equal to this 3 is equal to minus x squared minus y, and the imaginary part of this one, that's minus x squared y, is equal to this one that's simply 4. Then if we simultaneously solve this thing, we have this one that is y is equal to minus x squared, that is minus 3, and this one that is just rewriting this one another way of writing, so that the solution will be that is, for example, if we let this one, that is because x to the power of 4 plus 3x squared minus 4, if we let by using that substitution, that is let, for example, x squared is equal to a. So if we substitute x equal to a, we have a squared plus 3a squared minus 4. Then it becomes simple quadratic equation. We can have a solution there. The solution, I think the solution becomes 1 and that of minus 4. So we have to ignore minus 4 because the square of the square of a can never be identical with minus 4, so that then we have to take the positive part, that's simply 1, so that a square is equal to 1 and x is equal to plus or minus 1. Then if x is plus or minus 1, for example, if x is 1, what will be y? If it is minus 1, if x is minus 1, for example, one of the possible values of x which is obtained here, and if we replace it here in the place of x here, so that we have minus of 1 squared, that's simply minus 1 minus 3, which is minus 4. Even if we take minus 1 again for x, it is still minus 4, so that the values of x and that of y, which can make this complex number to be the complex conjugate of this one, or vice versa. That is when x is plus or minus 1 and y is equal to minus 4. So that this is the solution. The next one is question number 6, which is find the values of the real numbers x and y, such that x over 1 plus I plus y over 1 minus y is equal to 1. Again, solving the values of x and y, which can make this equation involving complex number to be true. The solution will be multiply by conjugates of each. That means in order to write each complex number in standard form, we have to multiply, for example, x over 1 plus I by the complex conjugate of 1 plus I, and y over 1 minus 2i by using the complex conjugate of this 1 minus y, which is 1 plus y. So that becomes x into 1 minus I over 2, where this is to be because the complex conjugate of this number and this one is already 2. Similarly, for the next one, we have y into 1 plus 2i, that is the complex conjugate of 1 minus 2i over 5. This 5 will be obtained by taking the square of the real part of this 1 plus the imaginary part of this complex number, which is 1 plus 4, that is 5 is equal to 1. Then the next one could be, in order to further simplify again, let us multiply both sides of this equation by the least common multiple of 25, that is simply by 10. When we do this, we have 5x into 1 minus I plus twice of y into 1 plus y is equal to 10. Then, in order to determine the y and that of x, we have to equate again the real and the imaginary part of this expression. So we have this equation that's simply 5x plus y, that is the real part. The real part from the first one is 5x times 1, that's simply 5x plus 2y times 1 is equal to the real part is this one, that's simply 10. And the next one, that is the imaginary part, will be minus 5x plus 2y times 2, that's simply 4y. But the imaginary part to the right of the equality sign is 0, therefore it is 0. Then when we solve this one simultaneously, if we directly add them together, 5x, we have 5x, it becomes 0, this is 6, and this could be 10, so that 6y is equal to 10, that is, I think, 5 over 3, or yeah, y will be 5 over 3. Then if we obtain one of these two, that's simply y. By back substitution, we can determine the value of the second variable, that is x. Therefore, the solution for this system of linear equation could be x equal to 4 over 3 and y is equal to 5 over 3. Therefore, when x and y are given here, this equation that simply will become satisfied. Or the sum of these two will becomes 1. The next one is question number 6D. Again, find the values of the real numbers x and y, say that's x over this plus yi over 3 plus I is equal to 2 over 1 plus I. A similar procedure from the previous one with a little complexity here. So the solution could be, first, let us simplify each term. That means let's write each of the three terms in standard form, that is z is equal to x plus iy form. So that just to do this, we have to multiply the first fraction by using the 2 plus y, that is 2 plus I, which is the complex conjugate of this one, and this must be multiplied by 3 minus I, and this one 1 minus I. When we do this, we have x into 2 plus y, 2 plus I over 5. This 5 will be obtained by adding the square of the real part of this one and the imaginary part of this one, that is 4 plus 1. And this could be obtained by adding the square of 3 and 1. And here, that is, I think there is 1 minus I over, that is 2 into, it must be 2 into 1 minus I over 1 square plus, that is 2, but these 2 can be cancelled by 2, and we have left only this one, that is 1 minus I. And then if we multiply again both sides by the least common multiple of 5 and 2, that's simply by 10, we have 4x plus y. If we multiply this one by 10, that means we have 2 times twice of x times 2, that's 4x, twice of x times y, I could be this one, that simply, and then this is y plus, that is, after multiplying, we take the real parts together and the imaginary parts together, we have this one, that's 4x plus y, the real part of this expression to the left of the equality sign, and twice of x plus 3y times I will be the imaginary part. And on the left, if we multiply both sides by 10, we have 10 minus 10i. Then let's equate as usual the real and the imaginary parts together. So that the imaginary from the real part, that's simply the real part of this complex number is 4x plus y. It must be identical with 10. And the imaginary part 2x plus 3y must be with the imaginary part of this one, which is minus 10. Therefore, solving this system of linear equation, we have the solution, that is x equal to 4 and y is equal to minus 6. That means when x is taken to be 4 and y is equal to minus 6, this expression or simple statement or equation will become satisfied. So that the exact values of x and y satisfying this condition or simple equation could be 4 and minus 6 respectively. The next one is question number 7. We are asked just to find the values of the real y such that 3 plus 2i plus, times 1 plus iy is in the first case real, that is real without complex, without imaginary part or simply whose imaginary part is 0, and second one is purely imaginary number with 0 real part. That means for the first one, first we have to expand this one and write the product of these two complex number in standard form, that in the form of z is equal to x plus iy. So that when we expand this one, we have This one, that's simply 3 minus 2y plus I multiplied by 3y plus 2. So that this is the real part, and this one is the imaginary part of the simplified the product of these two complex numbers. Therefore, what we are asked here is in the first case, we are asked just to determine the possible value of y, which can make this complex number to be real. That means which can make the imaginary part of this complex number, that is 3y plus 2, to be 0. That means the complex number will become real whenever it is imaginary part is 0, and the complex number is said to be purely imaginary number whenever it is a real part is 0. So that when we quit in the first case, that's simply for just to make this one real, we have to make this imaginary part to be 0, so that that means real when the imaginary part is 0, so that the imaginary part is 3y plus 2 is equal to 0, so that y is equal to minus 2 over 3. Therefore, whenever y is equal to negative 2 over 3, this complex number will be real without imaginary, or its imaginary part will become 0. Just to make its imaginary, we have to make the real part to be 0. The real part is 3 minus 2y, so that when it is 0, y must be 3 over 2. Therefore, whenever y is equal